The idea of R and S configurations in organic chemistry is very important, and there are other designations, for example, D and L designations, but the whole idea is that when we have a molecule, it is very important to know whether or not, once we move it around, if we actually have the same molecule. In other words, two molecules that look very much alike may actually be technically different enough so that we have two different molecules. They behave chemically different, for example. Okay. So what I'm going to do is show you first the general idea of R and S configuration. So we're going to do both 3D representation and the dash and wedge. Okay, so there's your 3D designation there. And then if I drew this other one in orange, that way we know that they are distinct. We could have a carbon here, and maybe we can draw that as a sphere. Then we would generally say that something in the plane here, we could draw this as an H. We would draw that here. We could draw this as a chlorine. Those two are in the same plane. The chlorine and the hydrogen are in the same plane. You've seen this before, probably. And then we could draw this designation as a bromine. And then maybe, I'm sorry, that should be a dash. We could draw that as fluorine. So that should be just a dash without that extra line. That's the dash and wedge format. Okay? And this is 3D. So you can see how they're alike. But what we want to do now is we want to make sure that we are describing things, because if this structure gets moved around, we want to make sure that it's the same chiral arrangement, or it's the same spatial or stereoisomer that we had in the first place. Okay? So let's start with the idea. Let's take this one now, and we're going to attach some things to it. And really what we're going to do is talk about the relative weight. So let's draw a second version of this one. And we've made it easy, and I'll show you why in a minute. We've made it fairly easy. And there's the guy in the back. Okay? Well, there's the concept of priority. And the concept of priority is this: that higher atomic numbers have higher priority. And we have talked a little bit about priority when we had branching, when we did nomenclature, for example. So what's the idea of priority here? We're going to label these now. But I'm going to make your job easy, first of all, and I'm going to put H here, the hydrogen, in the back. Okay? And let's redraw this just to make sure. So I have two versions here. So let's... Okay, a little bit off, but you get the idea now. I'm sorry. Now we have these two isomers here, or they will soon be isomers here. And we're going to draw H. And we draw the H in the back because that's actually a very good trick to learn when you're doing R and S configurations. Okay, so now what we're going to do is we're going to attach just some really simple things here. Fluorine, we could put here. Fluorine is 19. And chlorine here is 35, and then iodine, or iodine, is 126. And that's going to make our jobs very simple. So it is helpful here that we include the atomic mass of fluorine is 19, chlorine is 35.45, and then iodine is something like 126. Okay? That's going to be helpful for us. Let's switch those, however, or let's at least act like we're switching them. And we don't know for sure yet. Let's keep the iodine here, but this time let's put the fluorine on the left and then the chlorine on the right. Now to make our job simpler, let's make sure then the chlorine is what we called 35, fluorine is 19, and this is 126. Okay, so now we have these two arrangements here, and the R and S designations basically say this, that we rotate from highest priority to the next highest, and so on. If we rotate to the left, that's called the S designation, and by left we mean the counterclockwise, and then the R designation, which stands for right, is the clockwise spin. And this will help us determine if we actually have a stereoisomer or if we have exactly the same one. So how do we do that? If we go to this top structure here, our central carbon here, obviously, what they will tell you is put the lowest priority in the back. So that hydrogen there is what we call lowest priority because it has the lowest atomic number. And if you put it in the back, that makes things very simple. So again, this is lowest here, lowest priority. But now let's count from highest to next highest. And if we go up here, when we start with 126 and we go this way, this is what we would call an R designation, right? Because we are going in this direction. We're going, if we look at the face of this, remembering H is in the back, we have iodine 126, and then chlorine would be next, and then fluorine would be last. And so that's what we call the R designation for R and S configurations. If we do this again, but this time with 126, we see that this switched. And now we have what is called the S designation. And so that can be fairly simple until you have to rotate things and try to figure it out for yourself. But that's the basic idea of R and S configurations. Okay? But now we run into a different situation. And you knew that was going to happen. Now what we're going to do is, what if we have different connectivity? Or if we run into two structures that are very much alike. So let's draw our two carbons here. These are our central carbons. And again, we'll draw the hydrogens in the back in a minute, but let's call this one whatever let's hold off on that for a second. Let's now call this one CH2CH3. So we're going to put a methyl group, or an ethyl group rather. So that one comes out at you. And then this time we'll put a fluorine over here. Nope. Let's not do that. Let's put a C connected to H2 and connected to an N. Right? Let's put that. A little messy, but that's the idea. And this one, of course, comes out at you. And to make our jobs easier, though, we're going to put the H in the back. Let's color him red. Okay? But this time, and we can put iodine up here. That's fine. We can put iodine up here. This time, let's put CH2CH3 here. Again, that's coming out to the front. And let's put a C double bond O here. And then that might be an H. Okay? So let's look at what happens there. Because we don't have it as simple as we did before, let's go back here. When we did the R and S designation on this one, we could say, well, iodine and fluorine and chlorine, they're all different, right? All four. And so you rotate here. That's pretty easy. I, Cl, and F. We did that previously. But now we don't have quite that luxury, because now we have to make a choice. And so now, yes, we have iodine. We know that's going to be 126. Okay? But here you have to be careful. If you do it wrong, you're going to do it by the weight of this whole structure, and that's not correct. We don't worry about the weight of CH2CH3. But the reason we have to make a choice is because we have a carbon here and a carbon here. So what we do is we look for the next highest priority. Well, this carbon has a hydrogen attached, but so does this. No big deal. So who's next? We look at this one, and this one has carbon, which has an atomic mass of 12. But this one has nitrogen, and that has an atomic mass of 14. So now we can look at that, and now that's how we make our designations. Even though we have a carbon attached to both situations, we go down the line and basically we find where we get a separation. In college it's going to be a little more complex, but this is basically what we do. So now what do we have? We have 126, 14, and 12, and because of that, this is an S orientation, S designation. Let's make sure we draw the hydrogen here in the back. And we should have drawn them red, right, just so you can see it. Okay, that hydrogen is in the back, and so we look at the face of this, and do we have to make choices? Well, sure, because we have carbons here, and this is the next priority. That has a mass of 12, but when we look at oxygen here, that has a mass of 16, and so this time, again, we go from 126, and we would go this way again. So this second time we have another S designation. If you're having trouble with visualizing all of this, let's take this structure here, and we can imagine that there's a clock of sorts here. Okay? So really what we're doing is that we're saying, yes, there's this clock face here, and we could say 12, 9, and so on. Okay? And maybe give that a little bit of 3D aspect, if you will. But let's take that hydrogen as some kind of a support in the back. Okay, so that now you can see that there's some kind of depth, for example, so that little H is propping up this little clock here. Okay, so that's the idea, that that's always going to be the lowest priority if you have H. Okay, if you don't have H, then you pick something else with other low priorities. So that's the basic ideas involved with RNS configurations. Let's make sure we know that you can use the 3D model or the wedge and dash. Okay. The general idea is that you use atomic numbers for the first connectivity to the central atom. Okay. And so this was a pretty simple example. If the rotation goes from the highest to the next highest in the clockwise direction, we call that the R designation. But if we go this way, 126 to 35 here, right, then that becomes an S designation. There will be times when you have to make a decision about the connectivity, because if two of them are the same atom, for example, carbons here, we saw that then you go to the next connected atom. And so on this one it would be carbon, because both of them had hydrogen, and this one would be nitrogen. And so if we look at those atomic numbers, that gives us a way to determine which sequence to go in.